Hello. Just quickly share my screen and start the session. All right. Hello, everyone. Welcome to the 10th weekly discussion and doubt clearing session on the NPTEL course on concrete technology, NOC24-CE46, which is taken by Professor B. Bhattacharya of IIT Delhi. I'm Ashirvad Satpathy. I'm a PMRF research scholar at IIT Delhi, and what I do is I take these weekly sessions of 2 hours where we discuss the previous week's assignment problems that you have already submitted the answers to, and the deadline has already passed. And we also take up any doubts that you might be having regarding the previous week's lectures. There is another teaching assistant to this course. His name is Debojyoti. He usually takes his weekly discussion sessions of 2 hours on Saturdays from 6 to 8 p.m. And I take my weekly discussion sessions on Mondays from 6 to 8 p.m. Right? In today's session, we'll be discussing the week 9, assignment 9 questions, and we'll also take any doubts that you might be having regarding the week 9 lectures. The first question of the week 9 assignment was: creep happens in concrete when the stresses are beyond dash of the ultimate capacity, 30%, 60%, 70%, or none of the above. They've asked creep happens in concrete at what stress level at what percentage of the stress level of that of the ultimate stress capacity of concrete. Is it 30, 60, 70% of the ultimate capacity, or none of the above? At what percentage of the ultimate stress capacity can creep start to occur in concrete? All right, I'll first allow your microphone so that you can just unmute yourself to speak. Yes, I have allowed your microphones, so you can either raise your hands or unmute yourself and speak directly.
Yeah, this is none of the above.
None of the above?
Yeah, sir.
Right, that's the correct answer. Why would you say that? Can you explain? How is it none of the above? I mean, at what stress level does creep occur in concrete? Okay, Abdul, can you tell me so if this is the correct answer is none of the above, that's correct. But at what stress level does can creep occur in concrete? All right. Yes, creep can occur at any stress level. So therefore, there is no such relation as to at what percentage of the ultimate stress capacity can creep start to happen. Creep can occur at any stress level, and even even under its self weight. even under self weight, the concrete or any material for that matter, when the material changes, only the level of creep and the yeah, the degree of creep changes. But apart from that, creep can occur in any material at any stress level, and it can also occur under the self weight of the given material. So as we know that every material carries some weight, so creep essentially can occur all the time at even without any external application of the load. It can occur in a given specimen, right? All right. The second question was, it is a assertion and reasoning type of question. The assertion is that concrete shows less creep after removal of all the evaporable water from it. And the reason they have given is creep in concrete is related to the movement of adsorbed or interlayer water from larger to narrower pores. You have to answer if the assertion is correct and the reason is correct, and is this reason, the given reason, the correct explanation to the assertion given over here. The assertion is concrete shows less creep after removal of all the evaporable water. What is evaporable water? Can anybody tell me? What is evaporable water? Evaporable water is that water which is freely moving within the pores of concrete and can be evaporated out when the concrete is heated at 100 degrees Celsius or so. So when concrete is heated up to 105 degrees Celsius, like we do it in a oven, evaporable water gets lost, right? So the other water that will be present is only the non-evaporable water. Non-evaporable water will be chemically bound or adsorbed onto the surfaces of different phases, right? So evaporable water is that water which can be drawn out of the concrete when you heat the concrete up to 100 degrees Celsius. So what they are asking is concrete shows less creep after you remove the evaporable water from it. Is it true? And then the reason they have given is creep in concrete is related to the movement of adsorbed or interlayer water from larger to narrow pores. Can anybody answer to this question? Yes, anyone? Is the assertion true
Yeah,
and the reason true? And is it
the assertions and reasons are true.
okay?
That is, and answer is first one.
Okay, the first one is the correct answer. Yes. So, yeah, this is actually the correct assertion. When concrete, so we know that creep occurs in concrete due to the movement of the moisture inside it. the water and the pore water inside it. So when you remove the evaporable water from concrete, essentially the creep also reduces. And the reason they have given, again, it is due to the movement of water. So creep in concrete is related to the movement of adsorbed or interlayer water from larger to narrower pores. So when you remove the water from it, you essentially remove the water from the larger pores first because they have the least tensile force in them. So you remove the water from the larger pores first, and since the water is lost, there won't be any water left inside the concrete to for it to move from a larger to a smaller pore, which will result in creep. So when you remove the water from the pores, it might so occur that the concrete might get shrunken a bit. It might undergo a shrinkage, and now that it has already shrunken, there won't be any. I mean, the possibility of occurring creep will reduce in it. So that's the correct reason to it also, because we know that creep occurs due to the movement of the interlayer water from larger to narrower pores, and when you remove that evaporable water, creep will reduce. So the option 1 is the correct answer. Moving on to the third question, which of the below are correctly matched? And they have given a table, the factors affecting creep in the second column, and what is the effect of that factor on creep. Does it increase creep or decrease creep? And there are four factors. Decrease in aggregate modulus of elasticity increases creep. You have to mention if it is a truly matched or not. Decrease in aggregate modulus of elasticity increases creep. Increase in water to cement ratio decreases creep. Increase in temperature increases creep. Increase in load application age decreases creep. Which of these factors have been correctly matched to their effects on creep? Yes, anyone?
Increase in temperature, then definitely effect of creep will increase. That is
Okay.
third one. And another one, increase in load application age, that also decrease. The creep is decrease in that case. That's
Okay.
why 3 and 4 are correct.
3 and 4 are correct. And decrease in aggregate modulus of elasticity? How does the
Decrease.
aggregate modulus of elasticity affect the creep in concrete? Can you tell me also that?
In aggregate modulus of velocity decreases, in that case, creep effect will be increases. Isn't it, sir?
What did you say? Can you please repeat again?
That is, modulus of velocity decreases in aggregate. In that
Yeah.
case, effect in creep will be increases.
Yeah, right. So the creep will increase, right, when you decrease the aggregate modulus.
Yeah, yeah.
Yeah, that's also one correct answer. So 1, 3, and 4 are correct. And what happens when you increase the water to cement ratio? Does the creep increase or decrease?
Increase in water cement ratio, that is decreases only.
It
If it is
decreases the creep or increases the creep? When you increase the water to cement ratio,
water cement ratio,
does it increase the creep or decrease the
water
creep?
cement ratio is less because of it is related to the strength also. Because if this water
All
cement
right,
ratio is less, the strength
let
of
me
the
take you
concrete will
through it.
decrease.
When you increase the water to
Your
cement ratio, what happens to the pores? The pore volume increases or decreases? The volume, the porosity of the concrete increases or decreases? What happens when you increase the water to cement ratio?
Ports will increase because see
Increase,
what
right? Yeah,
yeah,
because
yeah.
you have more water than is required. Now that water will some of it will get consumed by the cement for its hydration, and the rest will just dry out, right, leaving pores behind, large pores behind in
and
the concrete structure.
and this water is occupying the concrete. That means afterwards it will leave as a void also. In that case,
Yeah, that
strength also.
yeah, so that will leave a void, and that will reduce its strength also. Now when it the porosity increases, what will be its effect on creep? Because there will be more movement, there will be more space for the movement of water now, because the porosity is increased. The pore size has also increased, right? So now there will be more space or more availability of pores of different sizes for the movement of moisture inside the concrete. So that will increase the creep. So when you increase the water to cement ratio, it increases the porosity, and therefore it also increases the creep as well. So this statement, except for two, all the three other statements are true, right? I'll just, I might have just, this is turned upside down. There's some issue with this picture. I don't know how it got flipped. Somehow it got flipped actually. Rotation. Anyway, I'll just delete this from over here. Um, let's not waste time on this. So yeah, as we are discussing, let's go over all these factors one by one. Decrease in aggregate modulus of elasticity. So we know that when um, uh, there is a, so it is essential before we discuss this factor about the effect of modulus of aggregates on the creep in concrete. We need to know that what part of concrete undergoes creep. Is it the cement paste or the aggregates? And it has been already discussed in the lecture as well. It is only the cement paste part, and more importantly, it has been seen from the research that the CSH gel present in the cement paste, cement hydration product, is responsible for creep in concrete. So it is only the cement paste part that undergoes creep in concrete and not the aggregates. Therefore, when you increase the modulus of elasticity of aggregates, their um, the load that now they can share from the concrete will also increase. So when you increase the modulus of elasticity, the load that is being shared by the aggregates also gets increased. So therefore, lesser load is being taken up by the cement paste. And when we have seen that when the stress is less, the creep is also less. So you want aggregates with higher modulus of elasticity so that your creep will also decrease in concrete. So I'll just mention it quickly over here. aggregate modulus of elasticity increases, load share on aggregates increases, load share on cement paste decreases, and that leads to creep decreases. So this is the chain of explanation for how the modulus of elasticity of aggregates affect the creep. When the modulus of elasticity of aggregates increases, the share of the load, or the part of the portion of the load that they can take, the aggregates can take, also increases, meaning that the load share being taken by the cement paste reduces, and when the load share reduces, the stress also reduces, and the stress, when the stress is less, creep is also less. So creep decreases when you increase the modulus of elasticity of aggregates. Same with when you increase the volume of aggregates. Essentially, we again know that the cement paste is the part which gets, affected by creep, and therefore, when you increase the volume of aggregates in concrete, that means that you're decreasing the volume of cement paste in your concrete. Now, when you're decreasing the volume of cement paste, the creep that is going to occur in concrete is also being decreased, because the volume is reduced, which the volume that is undergoing creep is reduced, and therefore the total creep in concrete will also reduce. So that is one factor with aggregates as well. The volume of aggregates increases, the creep reduces. Coming on to the second factor that they have mentioned, increase in water to cement ratio. Again, as I have already explained, increase, sorry, water to cement ratio increases, porosity increases, movement of moisture increases, and therefore creep increases. So an increase in water to cement ratio will increase the creep and not decrease. So this is a wrong statement. This is a right statement, and that's a wrong statement. Increase in temperature. What happens when you increase the temperature? It has been seen that when you increase the temperature, the creep also increases. Yes, because essentially, when you increase the temperature, the surface tension of the pore water decreases. Right? It is inversely proportional to the surface tension. We have studied this in physics, that when you increase the temperature, the surface tension of any fluid, or at least water, decreases with the increase in temperature. Now, when the surface tension decreases, it is easier for the pore water to move from a larger pore to a smaller pore. So the movement of pore water within the pores is now easier due to the reduced surface tension. And since the movement is easier now, the creep will increase. So the third one is temperature increases, surface tension of pore water reduces, movement of moisture is now easier, so it increases, and therefore creep increases. So this is the correct answer again. And the final one was increase in load application age. So if we have seen that as you increase the load application age, meaning that the time at which the age of the concrete at which you're applying a given load, so that has an effect on creep. How does it affect? If you apply the load at a very early age in concrete, the concrete is not hydrated much, and there is a lot of pore space. So it is expected to undergo a higher creep. But when you load the concrete at a later age, when it is already hydrated to a greater extent, and the volume is filled with hydration products and the porosity has reduced, then the creep that the concrete specimen will undergo will be much lesser. So as you increase the age of application of the load, so with increasing the age, the creep reduces, right? So this is different from the total age at which you're measuring creep. So if you suppose you apply a load on day one and you're measuring creep on day three and day seven, let us, for example, let us assume, then of course at day seven the creep will be more as compared to day three, right? But I'm talking about the application of the load, the age at which the load is being applied. That meaning that if you're applying the load at day 3 and in another specimen you are applying the load at day 7 from the casting and you're measuring the creep at day 10, or let's say 3 years, then you'll see that the specimen in which you applied the load at a later age, meaning that the specimen which you applied the load on day 7, that will undergo lower creep. So increase in the load application age decreases the creep. So that is again the correct answer. So the correct answer to this question is 1, 3, and 4. Right? I hope that that was clear to you. Moving on to the fourth question. It is again an assertion and reasoning type question. The assertion here is in statically indeterminate structures, creep relieves stress concentration. So the highlight over here is statically indeterminate structures. The creep relieves stress concentration. As the members are restrained, relaxation happens, which in turn increases the shrinkage stresses. So you have to say if the assertion is true and the reason is true, and if the reason is the correct explanation of the assertion, which is the correct answer. What is a statically indeterminate structure? Can somebody answer? This is uh, a part of your structural analysis in bachelor's course of civil engineering. What is a statically indeterminate structure? And then we'll discuss about stress concentration and so on. So before going over what creep does to statically indeterminate structures, let's first discuss what is statically indeterminate structure. Yes, can somebody answer? All right. Yes, can somebody answer, please? What is a statically indeterminate structure? Before we discuss the answer to this question is assertion is true and reason is false, right? So let's go over the statements one by one. A statically indeterminate structure is a structure in which the degree of restraint or the degree of redundancy is more than the available degrees of equilibrium or the equations of equilibrium, right? That means that when you have, let us say, a simply supported beam, so this is the hinged end and this is the roller end. This is a simply supported beam with a vertical load. So this is a statically determinate structure. How? Because the unknowns over here are, this is, let's say, P. So the unknown is R2, the vertical reaction on the roller support, R1, the vertical reaction on the hinge support, and since there are no, let me just do this also, and H1, right? So this is a horizontal reaction at the hinge support. So you have three unknowns. So unknowns are three, and equations of equilibrium. What are the equations of equilibrium? In order to find out these unknowns, those are when you carry out a force equilibrium, that is horizontal force equilibrium. Let us say that this is x-axis and this is y-axis. So summation of fx equals 0. Since this is static, so it is not moving anywhere. So the summation of fx equals 0. Summation of fy equals 0. In the y direction, you carry out a force equilibrium. So summation of fy equals 0. And summation of moments equals 0. So you also carry out a moment balance. So you have three equations, three unknowns, and three equations of equilibrium. So this is a statically determinate structure. You can easily solve this using the laws of statics in physics, laws of equilibrium in physics, and you can find out the unknowns. Now come to a fixed beam kind of a thing. You have a fixed beam and it has a vertical load. What are the reactions over here? You have a reaction R1 vertical, R2 over here. You have an H1 over here and H2 over here, and then you have two moments, M1 and M2, right? So how many unknowns are there? 1, 2, 3, 4, 5, 6. And how many equations of equilibrium are there? So you have three equations of equilibrium always, and you have six unknowns, right? So unknowns is 6 and equilibrium equations are 3. So this is statically indeterminate of degree 3. So this is just for your understanding how what is a statically indeterminate structure. You cannot obtain the values of these reactions using only the equations of equilibrium. So you'll have to add additional equations which come from the deformations, right? So you have to add additional equations on your own in order to find the unknowns. So that is how when you use the moment distribution methods and uh, other methods in order to find out the reaction forces in these fixed beams or statically indeterminate structures. We're not going over there in detail, but what I just wanted to highlight what is a statically indeterminate structure. Now coming back to this question, in case of statically indeterminate structures, creep relieves stress concentration. Now, what is the stress concentration? I'll just show you a very crude way of defining it. So let us say we take, now that we have established that a fixed beam is a statically indeterminate structure. When you make your structures, let us say this is a column, and then this is a beam, and then there is another column, and so on. In your house, this joint is a fixed joint, right? It is always, when in reality, there are no simply supported beams or so on. Only if you just, like in the olden days, there is a load bearing kind of a structure wherein you have supported the beam on walls. So that is only a simply supported beam. But when you're making monolithic structures, right? When you're casting the columns along with the beams and the slabs, then the joint is a fixed joint, and that will act similar to that of a fixed beam. Now, when you have a fixed beam and you apply the load, the vertical load, it will deform in a manner which is a little bit different from simply supported beam. So the curvature at the ends will be flat, and this curvature is always maintained 90 degree. So the beam supports are not allowed to move relatively to each other. If I just zoom it, if I just zoom this part, right? So even when it is unloaded as compared to when it is loaded, the curvature, sorry, the angle between the support and the beam at the beam ends is maintained 90 degree always. So there is that, this means that there is no relative motion or slash deformation between the beam end and support, right? So this angle between the beam end and the support has to be always to be maintained, and due to this fact, there is stress concentration in this region. So at the beam ends, the stress is concentrated, while at the other portions of the beam, the stress is being taken, and the deformation, and due to the deformation, the stress is being dissipated, right? Since this part cannot undergo any deformation, there's a stress concentration occurring at the beam ends. Now, what this causes is that there is a chance that due to increasing stress at these ends, the beam might break, beam might rupture. All right. But when creep occurs, what it essentially does is, since there is an increased amount of stress at these locations due to creep, it allows for the relaxation of this stress. How so? So the beam used to be initially like this, and now instead of maintaining that 90 degree, it will slightly maintain a lower angle now. So that means that due to the increased stress, there is a relaxation already occurred, and due to that relaxation, the beam hand now has undergone a slightly very slow, very low amount of relative deformation between the beam support and the beam end, and therefore, due to this relaxation, some of the stress that was being concentrated over here at the beam ends is released. So this is relaxation and release of stress concentration. So this occurs when there is a sustained stress inside a concrete member due to creep. That stress is released due to relaxation. All right. So the relaxation causes the relief of this stress concentration. So the first assertion is true. In statically indeterminate structures, there is a stress concentration, and creep relieves this stress concentration. So the first is true. And the second statement was, as the members are restrained, relaxation happens, which in turn increases shrinkage stresses. It doesn't increase the stresses, it decreases the stresses. And not nothing regarding shrinkage for now, but since the first assertion was regarding creep, so this should not be related to shrinkage. But anyway, it won't increase the stresses. Relaxation always reduces stresses, right? So that is why it is named relaxation. It makes the member relaxed, right? Relaxation reduces stress and not increase. So that is exactly why the reason is false and the assertion is true. So the correct answer to this question is this, the third option. I hope that was clear to you. The fifth question was, which of the following statements are true? Statement 1 is, in mass concreting, due to creep, there is a possibility of decrease in cracking. The second statement was, in tall buildings, differential creep in outer and inner columns may result in additional moments. Statement 3 is, creep results in loss of pre-stress in pre-stressed members. Which of these statements are true and why? In mass concreting due to creep, there is a possibility of decrease in cracking. In tall buildings, differential creep in outer and inner columns may result in additional moments. And the third statement was, creep results in loss of pre-stress in pre-stress structures. Which of these statements are true and why? Can you tell me? Yes, can someone answer this question? Abdul, Kailash, Pavitra, can you answer this question? Which of the given statements are true and why?
Statement one, it is false actually. Statement two and three is true. First one, in first case, in mass concreting due to creep,
Mm-hmm.
there is a possibility of decrease in cracking, but it is not like that. There is increase in cracking only
Okay.
for mass concreting.
Right.
Then the other two in tall buildings, differential creep is
Mm-hmm.
outer and inner columns are uh, result in additional movements. That is correct. That third one also creep result in loss of pre-stress in pre-stressed stressed. That also
Okay.
that's correct. Creep result in loss of pre-stress in pre-stressed concrete
Right.
structure. That means two and three are true. The first one is false.
Okay. Right. That's the correct answer, Abdul. Thank you. Oh, sorry. Yeah. Yes, that is actually the correct answer. So, as Abdul already rightly mentioned, in mass concreting due to creep, there is a possibility of decrease in cracking. That is a wrong statement. In fact, in mass concreting, creep further increases the chances of cracking in concrete. What happens is in mass concreting is, so by mass concreting, we mean that very huge elements. This is huge elements like dams, dam structures, etc. Right? So when the concrete elements are too huge, the surface is exposed to atmosphere, and therefore it can release the heat, right? At surface. Now, where does this heat come from? Due to the hydration reactions. We know that the hydration reactions are exothermic. They release heat when the cement gets hydrated. Now, but the surface is exposed to atmosphere, and therefore it has I mean, it is able to release that heat uh, onto the atmosphere. However, the core is at a higher temperature. So there is a thermal gradient from the core, which has a higher temperature, and to that of the surface, which is at a lower temperature. Now, when the heat is getting released from the surface is getting cooled down, and therefore it wants to shrink. Right? We know that the increase in temperature causes an expansion. The decrease in temperature causes shrinkage. I mean, it makes it to contract. It's a contraction. So this contraction, due to this contraction, due to the heat release, the surface is trying to shrink, while the core is still at a higher temperature, and therefore it wants to expand. So there is expansive stresses over here, meaning that tension, and there is compression at the surface. Now, what creep due to this difference, there is a chance of cracking because tension causes a cracking, and due to the thermal gradient, the surface can be still cool, and the core is heated up, and therefore that can induce a cracking in the mass concrete structures. What creep does is when this stress, this compressive and this tensile stress remains there for long due to creep, that can further increase the stress. As we know that that can so let us say there is some cracking that is going on due to the compressive stress coming from the contraction of the surface, right? Now, what creep can do is it will further increase that cracking. Sorry, I wrongly mentioned it will increase the stress. It won't increase the stress. It increases the strain or the deformation that at the same stress. So, due to the compressive stress that the concrete is experiencing due to the contraction or the cooling down of the surface, the creep can further increase that cracking due to this compressive stress. On the other hand, the tensile stress due to the heated up core inside the mass concrete structure, that might result in some kind of cracking inside the concrete structure, because as you know that tension, the concrete is weak in tension, therefore the thermal expansion will cause a tension, and that will cause a cracking inside the core of the concrete, and due to creep this cracking can further increase. So creep can further increase thermal cracking, right? So, therefore, the first statement is wrong. In mass concreting, due to creep, there is in fact a possibility of increase in the cracking and not decrease. The second statement goes in tall buildings, differential creep in outer and inner columns may result in additional moments. Now, why do we say that there is a differential creep in the outer and inner columns in tall buildings? For that, we need to visualize how the load is being shared by different columns in a given section. So I'm just drawing a rough diagram to explain it to you. This is a top view of a slab and column system, right? There is a column over here, there is a column over here, there is a column over here, and there is a column over here. And then there is another column over here, right? How the load is being distributed, this is the top view. So the load will be distributed somewhat like this. So the corner columns will take a load, lesser load than the center column, the inner columns, because the inner column is taking a load from the whole of the square around it, right? But the columns at the outer sections will be taking a load from not from the whole of the square, but a reduced part of the square. This part is reduced, right? This part is not being shared by the corner columns. So the corner or outer columns. Let us say if there's another column over here, then that will further take even lower loads. So corner or outer columns share lesser load as compared to inner columns. I hope you're getting it. So we know that when the load or the stress is lower, when load or stress is lower, reduces, creep also reduces, right? So that means that outer columns, lower creep, inner columns undergo a higher creep due to higher load, right? And therefore there is a differential creep that is being generated um, in the case of tall buildings. Now what happens is that there is this column which is the outer column, and then there is this column which is an inner column, right? Due to higher creep, the column would now take this height maybe. So it has sunken down, while due to lower creep, this column has only sunken down this much. So this is the initial part, and this is the final creep in these two columns. So that will induce curvature in the beams, and that will further increase the moments. So increase the moments, because due to the differential creep in the columns, there will be differential deformation within the columns and the beams, and therefore additional moments will get generated. So this happens in the case of tall buildings. So outer columns and inner columns undergo different creep, so that induces additional moments. The statement 2 is correct. And finally, creep results in loss of pre-stress in the pre-stress structures. This we have already studied in the lecture as well. In the case of pre-stress structures, due to the continued application of the pre-stress, there is creep that is being undergo, that the concrete or the steel undergo, and due to that, the the applied pre-stress is lost. So creep is in fact one of the losses, different kinds of losses of pre-stress and pre-stress structures, and therefore when we design a pre-stress structure, we take the loss due to creep into account, and therefore we design the structure to a higher load from that of the load that we want actually in the structure, because we know that some of the stress will get lost due to the creep and other factors like slippage and all that. So there are a lot of factors that affect the loss of pre-stress in pre-stress structures, and creep is one of them. and we take into account, we apply additional factor of safety in order to account for these losses of the pre-stress. So statement 2 and statement 3 are the correct answers. Moving on to the sixth question, drying shrinkage is completely reversible. The assertion is that drying shrinkage is completely reversible, and the reason they have given is after drying, if we pour water again on member, the water will be absorbed and shrinkage will be reversed. You have to say if the assertion is true and the reason is true, and is this reason the correct explanation of this assertion. Can somebody answer, please? Is drying shrinkage completely reversible? After drying, if we pour water again on member, the water will be absorbed and shrinkage will be reversed. What is the correct answer to this question? Yes, anyone?
In this case, both are false, actually.
Right, right.
This drying shrinkage is completely reversible, that is wrong. And after drying, we pour water again on member, the water will be absorbed and shrinkage will be reversed. It is not possible. It cannot, once it is shrinkage is happened, once it is after getting the dry, then it won't come back again. That means both are wrong.
Right, right. Thank you, Abdul. Yeah, that is actually the correct answer. Both of these statements are wrong. Drying shrinkage is not completely reversible. When drying shrinkage occurs, and when you pour water or you add an external source of water to the concrete specimens, it can undergo somewhat of a swelling and it can compensate for the somewhat for the shrinkage that has already been undergone, but it cannot completely recover all the shrinkage. It can only recover only a part of the shrinkage that is occurred in the concrete, and therefore drying shrinkage is not completely reversible. It is reversible only to a certain degree. Only some part of the shrinkage or the deformation that the concrete has undergone, that will be recovered, but not all the strain or the deformation will be recovered. So both the statements are wrong. Moving on to the seventh question, which of the following increase with increase in the volume to surface area ratio increase? All right. Is it creep, shrinkage, both creep and shrinkage, neither creep nor shrinkage? Which of the following increase with the increase in volume to surface area ratio? Yes, can someone answer?
Sir, display doesn't come. That question 7 displayed doesn't come.
Oh, you can't see my screen now?
Question 6 is still there. 7 not come.
Okay. All right, I'll just share my screen again.
Yes, okay, sir.
Yeah, you can see it now. Yeah, which of the
Yes,
following
sir.
increase with increase in the volume to surface area ratio? Is it creep, shrinkage, both creep and shrinkage, neither creep nor shrinkage? Can you answer?
Sorry, I lost the charge to my earphone. Can you hear me now? Is it audible to you?
Yes, sir.
Yeah, okay. Yeah. what is the correct answer to this question? Which of the following increase with increase in the volume to surface area ratio? What happens when you increase the volume to surface area ratio? Essentially, you're increasing the volume, right? With respect to the total surface area that is present. Meaning that your the phases that you have within your given material that occupy a larger volume compared to the surface area that they have. When the volume increases, the porosity will reduce. And when the porosity will reduce, how will it affect the creep? With the reduction of the porosity, there will be much lesser space available for the moisture to move, and therefore the creep will reduce. What will happen to shrinkage? When the porosity reduces, now it will be harder. Meaning that when the porosity reduces and the pore size also reduce, it will be harder for the water that is present within the smaller pores to come out, and therefore the concrete will undergo a lower shrinkage. So both creep and shrinkage will decrease when you increase the volume to surface area ratio, right? So the correct answer to this question will be neither creep nor shrinkage. And I have taken these view graphs uh, from the lecture slides, and you can see that this is for creep. As you increase the volume to surface area ratio, the creep reduces, right? And this is for shrinkage, ultimate shrinkage. And you see that as you increase the volume to surface area ratio, the ultimate shrinkage also reduces. So these factors don't increase, rather they decrease. The creep and shrinkage decrease with the increase in volume to surface area ratio. Alright. If you want, I can just mention it over here. So as volume increases, volume to surface area ratio increases, porosity, pore size reduces, less or moisture movement reduces, and creep therefore reduces, right? Coming over here, when the pore size reduces, difficult for the pore water to move out of small pores, therefore shrinkage reduces, right? I hope that was clear to you. Moving on to the eighth question. As evaporation happens, water moves from dash pores to dash pores. Larger to smaller, smaller to larger, water does not move, depends on other factors. As evaporation occurs, water moves from dash pores to dash pores.
It is water moves from larger to smaller.
Right, that's the correct answer. Yes, so when the water evaporates, it is easier for the water present in the larger pores to evaporate faster or to move out faster than for the water to in the smaller pores, because when the pore size is large, uh, the capillary forces within the pores are smaller, and therefore the capillary forces are the forces which are holding back the water and trying to keep it within the pore itself. Now when the pore size is larger and the capillary forces are smaller, it is easier for the water to move out. But when the pore size is smaller, the capillary forces will be larger and it will be harder for the water to move out. So what happens is, when evaporation is taking place, first of all, the larger water from the larger pores moves to the smaller pores, and the remaining water in the larger pores first gets evaporated. Once all the water remaining in the larger pores gets evaporated, the water from the smaller pores now has to come out and has to evaporate even further. So either when you increase the temperature, first the water from the larger pores evaporate, and then the water that has already moved out to the smaller pores, they start to evaporate at a higher temperature. So this is what is the right answer to the question. Moving on to the ninth question, which of the below are correctly matched? Decrease in aggregate modulus of elasticity. So they are asking about shrinkage. Decrease in aggregate modulus of elasticity increases the shrinkage. Increase in volume of aggregates decreases the shrinkage. Increase in curing period decreases the shrinkage. Decrease in relative humidity decreases the shrinkage. Which of these are correctly matched and how? I've already pasted the view graphs on the wrong slide, but anyway, that will be a hint to you. So you can just go ahead and look at them and tell me the answer. Or if you can just explain also, that will be cool. How do these factors affect the shrinkage? The aggregates modulus of elasticity, volume of aggregates, curing period of the concrete, relative humidity. Yes, anyone?
This decrease in aggregate modulus of elasticity, that is, of course, it is increases. That increase in volume for aggregate decreases, and increase in curing period decreases, because this moisture and it is all getting for the curing period. That's why the shrinkage will decrease. If it is exposed and higher temperature, if it is getting, there is chance for shrinkage more in the curing period. That's why most of the time the concrete, once we pour, then after we maintain at least for 7 days, 14 days, like that, we are maintaining the curing and all these things. Even moisten the surface. Thing. That is a very clear increase in curing period, then definitely it decrease the shrinkage.
Right.
That means that is mainly it is because of the temperature control for the ambient temperature and all these things.
Okay.
That in this case, 1, 2, 3 is correct.
Okay.
D 1, 2, 3. That is a D. That is decrease in which of
D is the
correct.
last one is the correct answer you want to say?
Last one it is wrong.
No, the 1,
Decrease
2, and
in
3 options are correct. You mean to say, right?
yeah, 1, 2, and 3 is correct.
Yeah. Yeah. So that is actually the correct answer. Yeah. Thank you, Abdul. Thank you so much. Yes, we'll go about all the factors one by one. Decrease in aggregate modulus of elasticity. Again, I mentioned in the previous slides about shrinkage. When you decrease the modulus of elasticity of aggregates, essentially you are decreasing the load that the aggregates will be able to take, and therefore the load on the paste will increase. When the load on the paste will increase, that will create a creep, that will increase the creep in the concrete. Again, coming back to shrinkage, when you decrease the aggregates modulus of elasticity, here I have taken a view graph on this slide, and you can see that this is the shrinkage, and this is as we move on from, these are the different types of aggregates, and they have shown that when the modulus of elasticity of aggregates increases, the shrinkage gets reduced. So you can see that granite, which has a higher modulus of elasticity and has a lower shrinkage than sandstone per se. So yeah, as you move on increasing the modulus of elasticity of aggregates, the shrinkage decreases. So this is the first one is correct. In fact, decrease in the modulus of elasticity of aggregates, the shrinkage increases. Or when you increase the um, when you increase the modulus of elasticity of aggregates, the shrinkage reduces, right? When you increase the volume of aggregates, again you can see this view graph. When you increase the volume of aggregates in concrete, the paste content gets reduced, and therefore shrinkage is occurring in the paste part of concrete. When the paste content gets reduced, the shrinkage will also be reduced, and you can see that this is the volume increase in volume of the aggregates and how the shrinkage is reduced, right? So increase in volume of aggregates again decreases the shrinkage. Coming to the curing period, as um, Abdul has rightly mentioned, when you cure your concrete specimens or concrete elements, essentially you're providing a water source from the outside, right? Now this water will go and fill in the pores, and therefore the deformation that the concrete would have undergone when it was not being cured will now be compensated by a further swelling. So when you cure your concrete, the shrinkage is reduced and is compensated by the swelling that is happening due to the external source or the external provision of the water, right? So increasing in the curing period decreases the shrinkage. That is again a correct statement. And the last one is decrease in relative humidity decreases the shrinkage. This is not correct. As you can see on the view graph on this, the third view graph, the three curves are increasing relative humidity, and you can see that as the relative humidity increases, the shrinkage reduces. So this is a inverse relationship. So when there will be a decrease in relative humidity, the shrinkage will increase and not decrease. So the correct answer to this question will be 1, 2, and 3. Moving on to the 10th question, what are the effects of shrinkage? And statement 1, 2, and 3 have been given. You have to select the correct statements. Increase of cracking in thin sections, loss of pre-stressed and pre-stressed members, additional moments in tall buildings. Which of the followings are the effect of shrinkage? Yes, can anyone answer this question?
Sir, can you please display the question, because in my window it is not visible, that question number 10. It is up to
Actually, it is. I
question
have
number.
shared the screen. Pavitra, is it visible to you? Can you just confirm, Pavitra? I have shared the screen and it should be working fine. I don't know. Understand? I don't understand why it is not showing to you. Can you just leave the session and reconnect again? I mean, can you
Yes,
please?
sir. I can try. I can try
Yeah,
later.
you can just reconnect and tell me.
Yeah, it has come.
Yeah. So, what are the effects of shrinkage? Increase of cracking in thin sections, loss of pre-stress in pre-stressed members, additional moments in tall building.
This
Perfect. Quick answer to
one.
this question. Yes, Abdul. Oh, you are going to answer this question?
Okay, that is fine. That is first one. It is correct. One, two, and three. All
Yeah,
are
all of these statements are actually correct, and we have discussed
all.
this in the previous sections, in the previous lectures sessions as well. That when there is thin sections, that the shrinkage can lead to excessive cracking in these sections, because um, we know that shrinkage in concrete induces tensile forces or tensile stresses within the concrete, and since the concrete is weak in tension, it will undergo cracking. And when there are thin sections, this cracking can propagate easily and in a very fast way, and can produce and can result in the failure of the thin sections. So the first statement is true: increase of cracking in thin sections can be caused due to shrinkage. Then there is loss of pre-stress and pre-stressed members. Yes, it is similar to
Yes. Sir, if it is a balanced section, what will the effect? If it is steel and concrete, if it is a balanced design, that means normally concrete is very weak for the tension, and the steel is taking out the load of the tension.
right.
In that, if it is a balanced section, that means within the stress and strain, and if it is
Right.
balanced section, the shrinkage will be less, isn't it?
Um, Yeah, I mean, you can say that when we're talking about reinforced structures, due to the shrinkage, there will be tensile forces, and some of that tensile forces can be transferred onto the reinforcement. So, as compared to plain concrete, the shrinkage, cracking due to shrinkage in reinforced concrete will be much lesser, because some of the tensile stresses will be taken up by the steel, the reinforcing steel. So if you're comparing plain concrete and reinforced concrete, then yes, for a given mix design, for keeping all other parameters same, if the concrete is similar in both the plain and the reinforced concrete, then yes, the reinforced concrete will undergo lower cracking, or low chances of cracking due to shrinkage, because some of the tensile forces induced by the shrinkage will be taken up by the reinforcing steel. Yes.
Yes, sir, correct.
Okay. Yeah. The second is loss of pre-stress and pre-stressed members. Yes, I was talking about this. It is similar to creep. When you apply a pre-stress or pre-tension, or I mean a tensile stress onto the steel, that um, tensile stress is being transferred onto the pre-stressed concrete as a compressive stress, and that will induce compression inside the concrete. Now, due to shrinkage, there will be tensile forces induced within the concrete, and that will compensate for some of the compression that is coming from the pre-stress. So yes, there will be loss of pre-stress due to due to shrinkage in pre-stressed members. I'll just draw this diagram so that this makes more sense. So let us say this is a pre-stressed concrete members, and this is a pre-stressing tendon, and this was applied with a tensile load, right? Tension. Due to this tensile load, there will be compression within the concrete, right? But due to shrinkage, there will be again tension in the concrete, not in the steel, but due to shrinkage, there will be tension in the concrete. So now the effective pre-stress will be C minus T dash, while the applied pre-stress should have been C. So this got reduced, right? So the applied pre-stress is C, while the effective pre-stress, due to shrinkage, there will be some induced tension, and therefore the compression that is coming from the pre-stress will be reduced. So the effective pre-stress gets reduced. So there is a loss of pre-stressed members due to shrinkage. So that is again a correct statement. And as we have discussed in the case of creep as well, there will be additional moments in the tall buildings because due to shrinkage, there will be some subsidence in the concrete members. Let's say we have cast two columns. And due to shrinkage, the outer columns are exposed to, sorry, this is inner columns, unexposed, inner, this is outer. So the outer columns are exposed to environment, let us say. So as temperature increases, thermal shrinkage might be undergone, thermal shrinkage or drying shrinkage. Drying shrinkage will be higher in outer columns and lower in inner columns. Right? So there will be a higher subsidence in the case of outer columns as compared to inner columns, and therefore an additional moment will be acted upon in the building due to shrinkage. Right? Outer columns are exposed to the environment and they undergo a higher temperature change and therefore a higher degree of drying shrinkage probably, and that will induce a higher subsidence in this or higher deformations in these outer columns, and therefore that will add an additional moment in the tall buildings. So the correct answer to this question are all the three statements are true. Right. That is the end of the week 9 assignment questions. If you have any more questions, then we can discuss. Otherwise, you are free to leave. The session will go on till 8 p.m. Yes, Abdul, do you have any questions?
No, sir. Thank you for the class. Anyhow,
Alright.
I just okay. Thank you very much.
Okay, you're welcome. Yeah, we can, I mean, since you're the only one over here, okay, is already left. Yeah, I mean, if you nobody has any questions, and therefore we can close the session for today, and we'll meet again on next Monday from 6 to 8 p.m. Okay, Sachin, you have joined just right now, and we're going to close the session. So if you have any doubts or queries, then you can ask them, or else, I mean, you have till 8 p.m. The session will go on till 8 p.m. We've already covered all the questions in the lecture, the assignment questions. Sachin, you're not audible, so are you trying to say something? Do you have any questions or
No,
queries?
sir. No, sir. No, really, no question, sir.
All right. Yeah. If you don't have any questions, then we can close the session for today, and we can meet again on the next Monday from 6 to 8 p.m. Meanwhile, if you
Okay.
have any questions, you can always put up in the forum, and you can also check this lecture session on YouTube. I'll share the link to you in the next class.
Okay, sir.
All right. Okay. Okay. I'm closing the session for today. Thank you.